Hello friends, today we'll be discussing objective 1 and the name of the chapter is Newton's laws of motion from H.C. Verma. My name is Hitesh Sharma and let's start with question number 1. A body of weight W1 is suspended from the ceiling and with a chain of weight W2, the ceiling pull the chain with a force obviously W1 plus W2 because that will be the total force bear by the ceiling, or you can just have a look at the diagram. W2 will be the weight of chain, W1 weight of the block or the body. So at this point tension will be W1 plus W2, only then the system can be in equilibrium. So tension or force by rope on the ceiling or force on ceiling by the rope will be W1 plus W2. Okay. The next question, when a horse pull a cart, the force that help the horse to move forward is the force exerted by the ground on the horse. Because the horse tried to push the ground in backward direction and that is the action, and ground apply a force in the forward direction on the horse. Okay. So with the help of force from the ground, or that force is usually friction, the horse is able to move. Okay. A cart accelerate on a horizontal road due to the force exerted by the road. Obviously, the friction is the reason why a car can accelerate on the road. Okay, so we can have a look at this diagram. This is a car, and friction by road will give you this acceleration. Normal and weight will cancel if the road is perfectly horizontal. So, friction by road will provide you the acceleration or speed up the car. In the next question, there's a block of 10 kg and there are two light spring balances. We have to find their readings. Obviously, tension in both the springs will be equal to 10 kg. So, reading is nothing but the tension. Reading of a spring balance is nothing but the tension in the spring or the spring force, that will be 10 kg in both. So both the scales will read 10 kg. Okay. In the next question, there is a block of mass m which is placed on a smooth inclined plane at an angle theta with horizontal. We have to find the force exerted by the plane on the block. Okay. So as there is no friction, the block will slide down the incline, but the acceleration of the block normal to the incline will be 0. Okay, so n will be equal to mg cos theta. We have just taken the component of m as mg cos theta perpendicular to the incline, as acceleration normal to the incline is 0. Otherwise, if there is some acceleration, the equation would have been n minus mg cos theta equal to ma. Okay, so the next question is, there's a block of mass m placed on the wedge. Whole system is accelerated horizontally and the block does not slip on the wedge. You have to find the force on the block by the wedge. Okay, so as we now know that the acceleration of block is horizontal and ay is 0. There is no acceleration in y direction. Okay, so we can say because the block is not moving down the incline, so it maintains a constant height, so no y displacement, no y velocity and no y acceleration. So mg, the forces in y direction will balance each other. There's a one force mg and another force is n cos theta, component of n in y direction, so both will cancel and n will be equal to mg cos theta. This is different from the previous question in which there was no acceleration normal to the incline. In this question, there is no acceleration in y direction. So in y direction, forces will balance in this question, and in that question, in the previous question, forces will balance in the direction normal to the incline. Okay. The next question, we have to neglect the effect of rotation of earth. Suppose that earth is suddenly stop attracting objects placed near its surface. A person standing on the surface of the earth Okay, so we don't have to consider the rotation of Earth. So Earth is still, and a person is standing on it, and the force of gravity is just vanishes at t equal to 0. So obviously it will remain standing as no new force is acting, just the previous force which was acting and which was balanced by normal reaction will be absent now, and normal reaction will also be absent, but the person will be at rest or remain standing. In the next, there are three rods which are joined to form a triangle. ABC 1 meter, and three particles carrying charges this much. The whole system is at rest in an inertial frame. The resultant force on the charged particle at A has the magnitude. Okay. One thing is to be noticed that the charges are at rest. Okay. So are attached to the vertices of the triangle. So net force, the resultant force on any of the charge must be zero. Otherwise, the system or the charges must accelerate. Okay. So as the charges are at rest, net force will be zero. The next question, there is a force F1 acts on a particle so as to accelerate it from rest to velocity v. The force F1 is then replaced by F2 which deaccelerate it. Obviously, the force need not to be equal. Okay, so they may or may not be equal, because they will, if they are stopping in same time, then they should be equal, and if they are taking different time to accelerate or to retard, obviously the force will be different. So option B is the correct. The forces may be equal and may be unequal in magnitude. So we'll go with option B. Next question. Two objects A and B are thrown upward simultaneously with same speed. Mass of A is greater than mass of B. Suppose A exerts a constant force of equal resistance force on the two objects. We have to find which will go higher and what will happen to them. Okay, so let's make a equation. Let's say the resistive force, as they are thrown upward, the resistive forces will be in downward direction. So acceleration of A, or we can say retardation of A, which will be in downward direction, will be net downward force upon mass. These are the only forces acting on this. So it will be G plus F by MA. Similarly for B, it will be G plus F by MB. As F is same and MA is greater than MB, mass A is heavier. Okay, MA is greater than MB. So obviously acceleration, or we can say retardation of B is greater than retardation of A. B will be retarded very fast and A will take more time to retard it to 0. So we can say option B is correct. A will go to a larger height, or A will cover more displacement as compared to B. In the next question, there is a smooth wedge A fitted in the chamber hanging from a fixed ceiling near the surface of Earth. A block B is at the top of the wedge. Takes time t to slide down the length of the wedge. If the block is placed at the top of the wedge and the cable supporting the chamber is broken at the same instant, the block, obviously now both will fall freely. Both will fall freely. So we can say the relative acceleration between them will be 0. Both will fall with an acceleration g, so relative acceleration will be 0, and they will be at rest relative to each other. So obviously the block will remain at the top of the wedge. We can also look at the diagram that a lift is falling freely. From the frame of lift, there will be a pseudo force of equal to mg, and mg real force will be downward, so normal is 0. Acceleration between block and wedge is 0, so block will be at rest relative to wedge. 12th is an important question. And there is an imaginary atmosphere in which the earth exerts a small force F on any particle in the direction of its motion. particle of mass m is projected upward, takes time t1 to reach its maximum height and t2 in return journey to the original point. Then we have to compare times. Okay, so let's take a look that a particle is thrown with a velocity u, and at the top its velocity is 0. In the return journey, obviously velocity at the top, which I have taken as initial velocity, is 0, and the final velocity is v dash at the initial point. So while moving up, the force from the atmosphere is upward and mg weight will be downward. So obviously it is topping, so we can say a is in downward direction. So we can write a as mg minus f by m. A in the upward journey is mg minus f by m, which is g minus f by m. And acceleration in the downward journey will be, as the motion is in downward, force will be force from the atmosphere will also be downward. So mg plus f by m, that will be g plus f by m. Okay, so it is the acceleration in upward journey, this is the acceleration in downward journey. So for the upward motion, to get time, we can use equation s is equal to vt minus half at square. This is another form of s is equal to ut plus half at square. Just replace u as uh, v minus at. Okay, you will get this equation. So s is equal to vt minus half at square. I have taken this equation because the final velocity in the upward motion is 0. So I can straight away say s is equal to half g minus f by m into t1 square. In the downward equation, I have used the equation s is equal to ut plus half at square because u is 0. So again I got s is equal to a downward, which is g plus f by m into t2 square. By dividing, we can say t1 is greater than t2 easily.